Welcome back to a new video about inverse Chebyshev response design using an LC ladder configuration. We continue with this example 3 with a bandpass filter design. We will see that in the calculations step by step and also verify these in SPICE simulations. So let's look at our example. The objective is a design of an inverse Chebyshev response passive LC ladder configuration for the bandpass filter. It must use a 50 ohm double terminated shunt input circuit. So we will see that shortly what this means. The generalized filter circuit is again shown here with the normalized source resistor and the normalized load resistor shown here. The specification for this example is that the maximum passband ripple must be 1.5 dB. The minimum stopband attenuation must be 40 dB. The lower passband frequency is 1 MHz. The upper passband frequency is 2 MHz. And the lower stopband frequency is 0.5 MHz, and the upper stopband frequency is 4 MHz. So we need to use these specifications for our calculations in order to determine the filter order, and then we will verify this after that in the simulations. So let's look at our solutions. Step 1 is the passband bandwidth and also the center frequency for this design. The bandwidth is the difference between the upper and the lower passband frequency. It's shown here. So we just calculate that using the given values here. And since we use the omega, we just multiply everything by 2 pi. So you get now this value here, 2 MHz minus the 1 MHz. You get now here the value for this, which is actually again 1 MHz. The center frequency is the geometric mean of the upper and the lower passband frequencies shown here. So this is the square root of the product. And when you now substitute again the values in omegas, so in radians per second, you get this one, so which is then approximately 8.886 mega radians per second, or million radians per second. Step 2 is the normalized passband frequency. This is the capital letter omega p, and also the normalized stopband frequency, the capital letter S of this prototype low-pass filter. We have discussed also in the Butterworth response and also in the Chebyshev response design that we need to start with the prototype low-pass filter and then move on by transforming our circuit to the bandpass filter. This is the formula for the bandpass filter design for the omega p. You can see that again the difference divided by the bandwidth, which is of course always 1. But the stopband normalized frequency, which is shown here, is determined by the upper and the lower stopband frequencies, the difference between that one, divided by again the bandwidth we have determined in step 1, which in this case 3.5 into the calculations. Step 3 is the calculation of the filter order N of this prototype low-pass filter, and that will be also again our the order for our bandpass filter design. We start with the epsilon P, which is related to A max. So A max is 1.5 dB. You just substitute that in this formula. You get now 0.6423. Epsilon S is related to the A min in similar form. You just substitute this 40 dB given in the specifications. You get now 99.99, almost 100. Now we can take this to parameters, epsilon P and epsilon S, and also our omega P and omega S, the capital letters, in this formula with this R cosine hyperbolicus. And then you just substitute the values here as shown here, and you get now 2.9826. Now we know we need to have an integer order, so we need to have at least third order here, so we take N is 3. Next step, step 4 is the bandpass scaling factor, which is then given by this KF bandpass, and that is in this case just the difference between the upper and the lower stopband frequency. That's for the inverse Chebyshev response design what we use. And we know it is 4 MHz minus the 0.5 MHz. That's just actually between the parentheses, in the parentheses, and times 2 pi to get to the radians per second at units. And that will be give us the 7 pi times 10 to the power 6 radians per second. Okay. That's of course 3.5 MHz. That's just the difference. Now let's collect these data. We have so far the center frequency, the bandwidth, and also the bandpass scaling factor. The Km is 50, which is our magnitude scaling factor, because we need to go from 1 ohm to 50 ohm because it is set in the specifications. Step 5 is the low pass to bandpass transformation. That is actually this circuit. We start this with this circuit, which is our low pass prototype filter for our inverse Chebyshev response. And for our transformation from low pass to band pass, we actually produce some transformations in the circuit. But before we do that, let's look at the table first, because we need to have a third order inverse Chebyshev. That's actually this table. And you see in this table some values for the A minimum, 20, 25, etc. We need 40, that means we need to look at this row, which is our final row here in this table, which is this fifth row. And there you can see the component values which are normalized, and normalized to stop band frequency of 1 radians per second. So you see C1 is equal to C3, which means this capacitor and this capacitor will have the same value. In this case, normalized is 2.83849 farads. And C2 here must be the 0.13211 farads. And the inductor here, again, normalized is 5.67, approximately 7 henries. But of course, those are not really practical values, so we need to scale it to the required component values for our specifications. Now, what is now actually this low pass to band pass transformation? Now, the low pass to band transformation is the following. For the circuit is the capacitors will transform in a parallel combination of a capacitor and an inductor. And we give that by the subscript P. And the inductors, any inductor you have in your circuit, will be then a parallel, the series combination of the inductor and the capacitor, which is shown here with subscript S for series. So we replace all the capacitors by a parallel combination of the capacitor and inductor, and all the inductors, just one in this case, by a series combination of the inductor and the capacitor, which is actually now shown here. Now, what do you see? You also see the following. The RS are prime, that means they are actually scaled up to 50 ohm. That's also for the RL, which is 50 ohm, so these two are 50 ohm. Let's go one by one. The C1 here is now replaced by this part. You see that here, CP, which is a parallel, but then due to the C1 coefficient, and LP due to that C1 coefficient. That means we have now twice as much components actually compared to the prototype low pass filter and this band pass filter. You'll see that for the C2, which is also a parallel combination of the inductor and the capacitor, which is then LPC2. That's actually sort of our notation to recognize which one is transformed. So it is actually this C2 is transformed in this inductor and this capacitor in the parallel form. And this is now the series combination of the inductor and the capacitor here because of this L2 due to this transformation. In the similar form, C3 is now transformed to a parallel combination of the capacitor and inductor. So we need to now determine the values of these components. So let's look at the step 6, which is the calculation of the scaled component values for this circuit, which is our final circuit. Okay, we know the values here. We also know the coefficients here, so we can now use the formulas. CP C1, due to the C1 is actually calculated with this one, which is C1 is again 2.83849 divided by the Km, which is 50, and also the Kf bandpass, which is 7 pi times 10 to the power 6. Now we now do the calculation, you get 2.581 nanofarads. Similar for the LPC1, but then you use the Km and also the center frequency, which is already calculated. You just substitute the values, or also the C1 as the coefficient, which is used for the CPC1. So you get now here 4.906 microhenries. Now CPC2 in a similar form actually, but then C2, which is actually this coefficient. So it's actually almost the same as the first one, just the coefficient is different. Then you get now 120.2 picofarads. And then in similar form for LPC2, use again the C2 here, and then you get now 105.4 microhenries. Moving on to the CPC3, which is then this, and that's actually shown here again using the C3 coefficient, but it's actually the same as C1. So just a copy of the C1 here, and also for this same inductor and the same capacitor values here. You see that. And the final one is our capacitor here in series due to that L2 coefficient, which is then here's 5.67699 henries. That's shown in the formula, and also the values we have determined before. And this will give you for the CSL2 the value of 981.2 picofarads. And now for the inductor here, LSL2 will be then 12.91 microhennies. As said before, the RS prime and also the RL prime will be 50 because they go from 1 ohm to 50 ohm by magnitude scaling factor of 50 ohm. So this for also the load. Okay, now we have all the components we need for this final design. So let's collect them together here. So we see actually the 8 components of the filter and also the source and the load. So in total 10 component values for our final design. And this is now the design, the final design in the SPICE simulator. The first one is the prototype low pass filter, which is our third order inverse Chebyshev response filter. And this is now the transformation from that to this filter by replacing the capacitor by a parallel combination of the capacitor inductor, and also here. And here is series combination of the capacitor inductor that's shown here. Now looking now at the simulation result for this circuit, and you can also see that these values are all here. So you see the 1 ohm is changed to 50 ohm, and here 2.838 farads will be changed to these two values according to the calculation we just done. So let's look at the simulation result and verify our specifications. Here we need it. So this is the plot. This is for the body plot, for the gain. You only see the gain actually, and what you also see is that there is no ripple in the passband, there is a ripple in the stop, and that's why it's called inverse Chebyshev response. It's also called the Chebyshev response type 2. So what we see, let's go one by one. The passband gain is 0.5. Why? Because at the passband frequency there's a gain of 1 over 1 plus 1, which is then a half, or 50 over 50 plus 50, which is 50 over 100, again 0.5. Now in dBs that's minus 6.02 approximately dB, which is also shown here. Now the next one is the lower passband frequency, which is at 1 megahertz. You see that actually here, and also you go down from this baseline, which is for minus 6.02 dB, to this value, which is the difference of 1.4163 dB, which is less than the maximum allowed of 1.5 dB. So that's also fine for this lower part. And for the upper part, in similar form, you see that at 2 megahertz, it's again 1.4188, again lower than the maximum allowed of 1.5 dB. The lower stop band attenuation, that's actually shown here, so labeled here in this pink box, which is going down from the baseline again to this value at this 500 kilohertz, so it's 0.5 megahertz. You actually go down at least by 40 dB, it's actually shown here. And for the inverse Chebyshev design, according to our steps, you actually achieve your step attenuation almost exactly, but you get more, let's say, headroom or less ripple than the maximum allowed in the passband. That is actually the effect of this step for the inverse Chebyshev design. Now, she said that actually this is sufficient according to specification for the upper stop band frequency. You also see that it's 40.0168, definitely at least 40 as said here. Okay, what you also see is that the center frequency is here, that is just 1.4142 megahertz, which is actually also what we have calculated, because we had omega center, which was 8.886 megahertz, and you now convert that to F center, which is then in hertz. You just divide by 2 pi, and you get now this expression, which is then 1.4143 megahertz, which is a small difference between this and that. That is just rounding of errors. So we can say all the specifications are met, and we have designed our inverse Chebyshev response design for the LC ladder filter, for this bandpass filter according to specifications. Alright guys, this is our example number 3 concerning the inverse Chebyshev response for this LC ladder filter, for the bandpass filter. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video.